all about gas laws. So, what are gas laws? Laws that govern gases. We've done solids and liquids and gases. Now we have a little bit of math and a little bit more on gases. So let's get to it. All your life you've heard of PSIs, or air pressure, peer pressure. But what is pressure? Pressure is just a certain amount of force in a given unit of area. So pounds per square inch is PSI. If you took the weight of your body, so you stood up on something, all of your weight, all of your force being caused by gravity would be settled where your 2 feet are. If you laid down, then all of your force would be spread out over a larger area. Same amount of force, larger area. So that would be less pressure. If your feet ended in tiny little points, and all you were standing on were those tiny little points, then that would cause a great deal of pressure. So, put one nail underneath your body, and the pressure would cause the nail to go into your skin. Take lots and lots and lots of nails and let them all support your body at one time. You've spread out that same force over a greater area. You can do that. And if you're ever in the McWane Center down in Birmingham, they actually have a nail bed that you can lay on and it'll lift you up in the air. But that's what pressure is. What I need y'all to do is I need y'all to get all of these things in your notes. This 14.7, the 1, these are all just units of pressure, and they're all equal. So in other words, there's 14.7 psi in 1 atmosphere. There's 760 torr in 1 atmosphere, so on, so on, and so on. Hit pause, and then after you're done getting these in your notes, go ahead and hit play again, and we'll pick up. PSI is what we typically use for tires. So you'll probably see that on like bike tires or car tires, something like that. Air compressors, if you have one at home, maybe your dad has one, they usually report in PSI. Atmospheres is something we made up. Atmosphere is the amount of pressure at sea level at a certain temperature. We just wanted a unit that had a nice 1 to it, so we came up with atmospheres. There's a guy named Torricelli, and a Torricelli is the Italian who came up with something called the barometer, and so we named one unit after him. The torr and millimeters of mercury are actually the same thing. You will see a barometer, oftentimes a mercury barometer, in weather offices, in science labs, things that really want a super accurate air pressure will have a mercury thermometer. And what it is a tube, and underneath that tube is a great big pile of mercury that's open to the air. And as the air pressure pushes down on the mercury either goes up the tube, or if it's not pushing quite as hard, goes down the tube. Kilopascals is the SI unit. That's a unit that we'll use a lot. It's the one they use in Europe, so they don't use PSI. And if you look on your tires, either on your bike tires or your car tires, you will see that it has a pressure both in PSI and also in kPa. If you look at your tire pressure gauge, like this one here, you will notice that it has a unit both in PSI and kPa. The last one is millibars. Millibars are used by weathermen and by engineers an awful lot. It's very, very similar to kilopascals. It's just off by a power of 10. We measure pressure using a barometer. Now, your grandparents may have a barometer hanging on their wall. Maybe you've seen one of these. This is a barometer that uses air pressure to push against a spring, and when that spring gets mushed in, it turns an arm in a dial, and it measures the air pressure. Normally, grandparents, I don't know why, but a lot of them have this on the wall, and it tells you the temperature, and it tells you if the weather's changing, because if the pressure's low, then that means that there's a storm. If the pressure's high, that means it's fair weather. And if there's somewhere in between, it means it's changing, which is exactly why this says what it is. If you have to measure the pressure inside a container, like could be you, right? You're a container and you have blood pressure, or inside of a tire, we use something called a manometer. You may have heard of a sphygmomanometer. A sphygmomanometer is a blood pressure cuff. That's the one that we use to measure the pressure inside of you. All right, so I've got a couple laws for you here in the beginning. Boyle's law. There are three things that affect air pressure. There's pressure, there's volume, there's temperature. So he could only study two at a time because he wanted to study the relationship between one thing and the other thing. So you got to leave the other one out. So he held temperature constant, and he looked at the relationship of pressure to volume. So looking at the relationship of pressure to volume, he found there was an inverse relationship, meaning as one goes up, the other one goes down. And an example of that is a syringe, and I actually have something to show you, kind of an example. So this is a container, and if we change the volume at all, then we should get a different pressure. So let's see. Right now, the pressure is 24 atmospheres. If I take and make the volume bigger, you'll notice that the pressure goes down because the same molecules take up more space, and so those molecules running into the side of the container is what generates the pressure. When those molecules slap into it, then that generates pressure. So if I make it occur over a larger area, the pressure gets smaller. If I make it occur in a smaller area, the pressure goes up. By the same token, I can try to drive the pressure up and down, and by changing the pressure, it changes the volume. So you just see the connection between those two. Charles' law is up next. Charles wanted to look at the relationship of volume and temperature, so he held the pressure constant. When he looked at that, he found that there was a direct relationship, meaning if he changed one higher, the other one went higher. Now, the thing to keep in mind here is it has to be in Kelvin. It has to be in Kelvin. So you all have already done this before in your life. You've taken a balloon and probably put it in a freezer at some point, and the volume gets smaller. Well, why is that? Well, same amount of gas molecules inside, they're just slower. And when things run into the side of the balloons more slowly, they create less pressure. By the same token, if you had heated them up, then the volume would have expanded, because the pressure is not changing so much because the pressure inside the balloon is trying to match the pressure pushing down on the outside of the balloon. Since the balloon can expand and contract, the pressure remains relatively constant and the volume changes with temperature. The last one, Gay-Lussac, he wanted to look at the relationship between pressure and temperature, and so he held volume constant. So an example is a ketchup bottle. If it's been in the refrigerator and you take it out and it warms up a little bit, and then you take the top off, what happens is the glass can't expand, or the plastic can't expand, but what happens is the air pressure builds up inside, and sometimes it'll kind of like spray out some ketchup and usually get it all over the place. So not a ton, just a little bit. Spray cans work the same way as like a can of paint or a can of hairspray or anything like that. Could be a tank of propane on the gas grill that you have at home. When you open up that nozzle and let the gas out, as the pressure goes down inside the tank, the temperature goes down as well. It actually gets cold. By the same token, if you increase the pressure inside that tank, the temperature would go up. And actually, that's exactly how an air conditioner works. It uses gas laws and pressure to, if you change the pressure, the temperature changes as well. So let's look at an example of that. So we're just going to look at temperature versus pressure. So let me change the temperature. And if you notice, the gas molecules really get slower. They get really slow. And when they're really, really slow, of course, the gas molecules just aren't hitting as hard, and so there's less pressure. By the same token, if we jack the temperature way up, we would see the pressure increase. So we see that as a direct connection. If we tie all three gas laws together, Boyle's, Charles, and Gay-Lussac's, then we get the combined gas law. Now, if you looked on the back of your periodic table, then you will see this gas law. It's the relationship between pressure, volume, and temperature. Realize you won't have to memorize this equation, you'll just have to be able to use it. We'll do some examples with this in class, and we're also going to do some examples here for your homework here in a minute. Whatever the pressure on the left is, if it's atmospheres, then the pressure on the right ends up in atmospheres. But if the temperature has to be in Kelvin, so don't let me trick you. Remember, the temperature has to be in Kelvin. So all you have to do when you're doing this is work on, I'll give you a pressure, a volume, and a temperature to start with. Then I'll give you a pressure and a volume, and you find the temperature. Or I'll give you a pressure and a temperature, and you find the volume. I will give you 5 of those 6 variables, and you have to find the last one. The combined gas law just describes what happens when you change one factor, what happens to the other factor. Time for an example. 15 liters of gas, that's the volume. Pressure, 19.3. Temperature's constant. Now there's 2 things you can do with a constant temperature. You can either leave it out altogether, or you can just make up a temperature that you want to put in. 112, doesn't matter, because the temperature is not going to change. The new pressure is 38.6 psi. What is the new volume? So how do you go about solving this? So remember, it's PV over T is equal to PV over T. This is time 1, 1, 1, 1. This is time 2, 2, 2, 2. So if you go back and look at the problem says 15 liters at 19.3 psi. So pressure 1 is 19.3 psi. Volume is 15 liters. And I'm just going to leave the temperature out, is equal to, and I'm going to do this time 2 stuff in pink. The second pressure, it said, was 38.6. And the second volume is, we don't know. So you have to solve for V2. So however you do it algebraically, however you learned, you'll get that the new volume is 7.5 liters. How did I do that quickly? Well, 19.3 and 38.6, you ought to be able to see that the pressure is doubling. So if the pressure doubles, then the volume is inversely affected. So it gets cut. The inverse of double means 1 over double means a half. So what's half of 15? 7.5 liters. So the new volume would be 7.5 liters. That's all you're doing is just plug and chug. Make sure the temperature is in Kelvin. The last gas law is Dalton's gas law. In Dalton's gas law, it said basically if you have a mixture of gases, oxygen, neon, whatever, then when you put them together in a container, each one has their own individual pressure because each one has gas molecules running into the side of the container. So the total pressure is just equal to the sum of the individual pressure.